Hello everyone. This is our day 3 of machine learning with Python. Today our major focus will be covering what we haven't covered before, the regression and also the day 3 contents and supervised learning. Yeah, just as I said, we last time yesterday we talked about line classification algorithms. And that's too much for one day's workshop. So we leave the regression and the regularization to today's contents. And later I will discuss the unsupervised learning, introduce some algorithms for dimension reduction and clustering. So for this workshop, I think the most important part is that we get some idea about what's the algorithm and what they are doing. We also have this practice using Jupyter Notebook. And that part is to try to give you the tool set. And the slides is to give you the mindset, like you understand how it works, so that probably in your later research, you can choose one algorithm and then train your model and make the prediction or other applications. So still at the rotation of the slides, everything with the arrow will be a code or pseudocode, and the link is underlined. For the workshop, we have a 10-minute break every 45 minutes. So for today, it's unsupervised learning. As this comics shows that we don't have a supervisor, right? And everything will depends on the data itself. We don't have a label. So for these two topics, dimension reduction and the clustering, they don't have the label. But let's get a really quick summary about what we have learned yesterday. So we have talked about 9 different classification algorithms, logistic regression, a really simple linear classifier, and the KNN, which is very intuitive, that we just calculate the distance between a new instance to the all the examples, and then try to get a majority vote. What's the class this instance should be? And the naive Bayes supervised machine is some tree-based method, decision tree, and also the bagging version, which is a random forest. And we learned something about the boosting, how to make the weak learner to form a strong learner. So this is also called the example learning, that we use the wisdom of crowd. And then lastly, we talk about the neural network for the classification. And we also do that, like try those algorithms in the Jupyter Notebook, try to classify the samples to different breast cancer subtypes. So we also learn for the classification problem, what's a loss function. Usually we use the cross entropy loss function, which is showing as right. So we start from the logistic regression, which is a binary classification problem, and then we generalize the entropy cross entropy to multi-class part. For example, here is the definition that we use the true probability distribution, which is one hot. Like for a given instance, the true label is either 1 or 0, and times the predicted probability in the log form. So the probability predicted probability will be generated by the classifier you use. We use the logistic regression to introduce the concept of performance measure. So for example, we have covered that accuracy, that how many true predictions you made. And in reality, for example, for the binary classifier, we have the true or false, which is like the actual label. And we also have the predicted label, like true or false. So in So as a result, we will end up with a table which is called the confusion matrix. This table is more informative than accuracy alone, because we know that when your data is imbalanced, the accuracy probably will not tell much. And based on the table, we define the precision recall, which is more useful when you have an imbalanced data set, and based on the probability, or when we try to change the threshold, we can get many confusion matrix, and thus we can plot the ROC curve, AUC curve, AUC, which means the error under the curve, and also the precision recall ROC. So this is how we try to measure the performance of a classifier. So lastly, we are a workshop focused on the practical side. We also learned how to use the scikit-learn package. Specifically, we try to split the data set into training, testing, and we use the functions from this package to evaluate the performance of different classifier, plot the ROC curve, and we for the really simple example, try to classify your samples into 2 different breast cancer type, which on that task, most of the methods perform very well. And we also move on to a more difficult classification problem where the samples are not linearly separable, and then we try some method on that. And later, lastly, we see something about overfitting and fitting when we use the decision tree and do some parameter tuning. So this is what we did yesterday. And so I have to mention that the scikit-learn website, they have a really good documentation. So I will strongly recommend you guys to go to the website, check what's in there, especially when you are trying to find the usage of some function. Don't try to write your own. First, you just go to the website and see if there is any available function for you. So today we are going to learn another type of supervised learning regression. And later we will talk about clustering and dimension reduction. So for the supervised learning, as we have seen before, that we have this label. And last time we talked about when the label is discrete, it's categorical. So at that time, it's a classification problem. We want to predict what's Y based on X. And this time, what if we have the target as a numerical value, like it's a continuous variable from, for example, here, I need 0.9, -5, 28 or something. So still, we have this label. We actually can try to name a function that make a prediction based on X. And this, when we have this numerical value, it's called a regression. So here it's the algorithms we are going to learn today. So first we start from the linear regression and then extend it to others. So it's worth noting that when we learn the classifier, we mentioned the support vector machine and also the boosting trees, the random forest. So basically those are for classification. But it turns out that those methods are really, it's not only restricted to classification. We are going to introduce their usage in the regression. So we start from this linear regression, which is a statistical model, and it has been well studied for years. And this linear regression probably you have experienced. Probably in your high school, you first learn how to what is the function you dealing with this linear regression. So linear regression, this topic was invented maybe 300 years ago, like Gauss, the famous mathematician, tries to learn what's the relationship between the children's height with the parents' height. So they actually find that there is like a linear relationship there. But anyway, we just take a look at this picture. What is the linear regression is that we want to make predictions based on the independent variable. So the dependent variable is our observation, is our label. So it's y here. And we simply want to draw a line, like this line, linear regression, that can describe all the data points well. And if we extend this single univariate problem to a multivariate problem, we simply try to predict y based on the linear combination of our features x1 to xn. So if we write it in the matrix form or in a vector form, we can simply think, okay, y, which is our predictive value, equals to a function, and this function is a dot product between two vectors. One is our parameter, and one is our variable. So if we train this model, we simply want to find a parameter set theta that can best fit the data. So when we talk about the best fit, we want to have some numerical measurement describing, okay, what is actually the best fit. So here is like the two popular version to describe the fitting. One is called the MSE, the mean square error. So basically, it will calculate average of this is your predictive value, and this is your true y value. So you take the difference and make it a square, and then average it over all the instance. So this is called the MSE. So as you can think that when we have a best fit, this value should be as small as possible, right? And another measure is that we just replace the square with the absolute value. So this is called mean absolute error. And these two are, both of them are very popular and very widely used. And but I have to say that the MAE should be should be more robust to the outliers, because when we know there is a very huge value of a single sample, the MSE will be driven to that huge value. So MAE is more robust. So if we take a look at this inner part, this is actually called the residue, the error residue. So when we have this minimize the MSE, we actually tries to make the line to have the to have this residue as small as possible. So this is also called the best fit. So luckily, this formula has a numerical solution or an analytical solution that we can actually derive the theta based on x and y, which is our feature and the label. And it has shown that the theta hat, which is the estimate of the parameter, is unbiased estimator. So unbiased means, okay, if we believe there is a true theta, and on the expectation level, this theta hat should equal to the true value. So this is a very simple model that we model the linear relationship, but sometimes our data don't have this particular linear relationship. For example, this figure showing here, we cannot find a single line that aligns the trajectory of all the data types. But instead, we probably think, okay, this seems to be more like a quadratic form of the relationship here. So this leads to the another topic called the polynomial regression. So basically, if we have x1 and x2, and we just focus on this one order of linear relationship. Basically, we have this beta 0 plus beta 1, x1 plus beta 2, x2. But if we want to raise up to the power of 2, for example, we allow the interaction between x1 and x2, or we allow the quadratic form of some feature, we actually can add more features to the model. Still, if we treat them like x1 squared as a different features, like this is still within the linear regression framework, because what we have is still a linear combination of these features, the old feature and the new features. So one thing I should mention that beta 0 is something we call the intercept, and the beta 1, beta 2, those parameters is called the slope. And for this polynomial regression, if you have a lot of features, you should be aware of the combinatory expulsion in the features. For example, if you have n features, so the number of the second order term should be n times n minus 1 divided by 2. And then if you have a higher order, so this will grow exponentially. So the third topic is about the support vector machine, support vector regression. So last time we learned the support vector machine is trying to find a margin that can separate these two clusters, and also we have the margin as big as possible. And also sometimes we don't have this ideal case that it separate everything well. There are always some margin violations. For example, some dot, although they belong to class 1, but they are more closer to the class 2, and you cannot find a single line to separate these two clusters. So this is called the margin violation. So it turns out yesterday we can write this problem into a constrained optimization problem using this object function, that we want to maximize the margin, which is just trying to minimize this part of term. And we want to reduce, like we want to limit the margin violations, because this is what we want, that we cannot allow too many violations in the classification. Otherwise, those are just a misclassification. So we will add this C, which is the hyperparameter, and the term, which is the violation distance. So for the supported vector machine regression, instead of trying to find a street that fits that separate two clusters as far as possible, this kind of task is trying to find a street that include every possible instance, and also limiting the margin violations. So this can also be written into a constrained optimization problem. And here we have the very similar optimization function. And remember that last time we talked about support vector machine, it's a linear classifier. We try to find a linear combination or the hyperplane to separate two clusters. But there is also some kernel trick, like we can use some polynomial or the similarity function to make SVM handle the nonlinear separable cases. So this type of tricks is also applicable to the SVM regression. So in the later Jupyter notebook practice, we are going to talk about one potential usage of SVM when we're dealing with the nonlinear regression problem. So so far for the nonlinear regression problem, we can use a polynomial regression to solve it. We can use a support vector machine to solve it. And also we can use the following advanced algorithm to do that. For example, one is the tree-based regression. So yesterday we talked about it's kind of like trying to find the region divisions, so that at each region we will have the class as pure as possible. And then actually this can also be applied to regression, that each of the region, if we separate it well, this region will have this numerical value. Just calculate the average of the numerical value as the representation for this region. So in the right part, we can see the decision tree regression is always trying to find a stepwise function. So for example, for this region, it always have this y value. And then for another region, it goes down to another value and so on. So within each region, the value is always constant. And very similar to the tree-based like classification problem, we have this loss function. If you still remember, last time for the classification problem, we want to have this part, the MSE part, is replaced by the Gini index, and here is actually we just simply replace Gini index with the mean square error and try to optimize this function, and then we end up with the decision tree regression. So decision tree is sometimes can be a weak learner. It can probably overfit to the data. So we also have one technique called the boosting that tries to make our prediction more accurate. So there is a gradient boosting machine that can actually make the predictor work better iteratively, learning from the error. So this kind of algorithm tries to improve iteratively by learning from the prediction error. So for example, we first fit a decision tree to the data, and then we have some results, prediction results. And then for the next decision tree, because this algorithm is learning sequentially, for the next one, we want to learn, okay, for the residues you make, can we fit another decision tree to learn it? So if we can do that. And then after this two step, we will have a new algorithm, that's the F2, which is a new regressor. It's actually equals to the first decision tree and plus the second decision tree. Sometimes we also want some like learning rate or decay or something, but in general, it's like a combination from the first decision tree and this newly learned decision tree. And then we can repeat this whole process until some mechanisms tell us to stop. For example, when you use the cross-validation, then you find, okay, the MSE or the performance measure shows this part is already good enough. So probably at that time, you should stop and then use the learning model to make predictions. So on the right is actually a GIF image showing how the gradient boosting machine works. So it can be seen that this part is doing. Let me see if I can make it. Yeah, it's moving. So. Yeah, so it shows that at each of the iteration, it will adjust the prediction, and then later we will see, okay, the learned regressor is quite close to the true function. So you can see that this process is trying to approximate the true pattern, although it didn't do well like at the very beginning. We only have like a very strange curve, but after you iterate, then from the mistake you make, you can actually try to approximate the original function using this procedure. And so basically this means the prediction the prediction works, and we can use it to make new predictions. So lastly, we have this neural network. Still, this is what we introduced yesterday, that we use it to make the classification work. And the neural network is actually a very universal function approximator, just as we have seen in the gradient boosting machine. We try to use the tree method to approximate the true function. And neural networks is actually one can also be regarded as this type of machine learning algorithm. So unlike the neural network we talked about yesterday, which use the sigmoid function to make the predictions, and this part and also for the classifier neural network, we have the loss function as a cross entropy. But for the regression, we will have this MSE as a loss function. So usually we prefer MSE over MAE simply because MSE has a nicer derivative. It's in the square form, so we can write we can calculate the derivative very easily. But sometimes MAE is also used. And I always want to, like, when we talk about neural network, I always want to compare it with the very simple model we have learned. For example, neural network for the classification, we compare it with the logistic regression. And for this part, we actually can compare it with the linear regression. So for linear regression, we have this formula, which is the linear combination of other features and the plus intercept, or sometimes we call it as a bias term. So it actually can be regarded as like a single layer neural network that don't have an activation function. And the deep neural network is actually showing like a more complicated structure that each of the layer is a linear combination of the features and the bias term, and then with new with the activation function, and then after that we have another layer, so which also forms to be a linear combination, and then goes to another layer, and then we end up with the final output. So it's like in a hierarchical structure, but for each layer, it's always a linear combination with the activation function. So so after we learn so many algorithms, I would like to introduce a concept that we have seen before, the overfit or underfit issue. Actually, this can be this can be something we should care more about during the model training and testing thing. So for example, when your model is very complex, so when we say model is very complex, we can think we can measure the complexity using the number of parameters in your model. For example, the decision trees, or in the neural network, you have many nodes or many sub-trees, and each of the nodes contains a parameter. And then those kind of model is more complex than the simple linear regression. So as your model complexity goes, the learning ability becomes higher. But so for example, just to take the classification problem as an example that we tried yesterday, for the non-linearly separable. Linearly non-separable cases, the logistic regression doesn't perform well, but the neural network or random forest seems to be pretty well because they are more complicated. So the learning rate means, okay, we can learn more complicated problems. So as the model complexity goes, we probably can see that the training error and the testing error, both of them will decay. But at some point, for example, when your data doesn't support the more complicated models, your training error still goes down, which means your model can overfit the training data, but your testing error goes up. So that means the model overfit and don't generalize well to other new cases. So at this changing point, we want to stop. We want to, okay, we are satisfied with the test error and in this case, we believe the model has a strong learning ability and can generalize well. So this is like the boundary, so called the best fit. On the left, we probably see the model is underfitting. On the right, we probably see the model is overfitting. So we want to like make a compromise between so make a compromise and stay here. So actually, this is related to in statistics. We call it has a bias and variance trade-off. So for the underfitting, it has low variance and a high bias. So the high bias means, okay, the model don't provide accurate results compared to the truth. So it has a large deviation from the truth. Because they are as simple, so probably in the newer cases, they will generate the better results. So the variance is low. And for the overfitting, it's that they have a low bias, but a high variance. So for example, the low bias means when you train on your training data, and then they generate as accurate results as possible. So the bias is low. But when you have a new data, for example, the testing, it cannot perform well. So under this case, it's called the high variance. So it's overfit. So ideally we want the no bias, the no variance, right? Because we want to, okay, the model is good, make predictions well on this particular set. And then for every new data set, it also makes good predictions. So this is what we want. We want everything is on target, but sometimes we on this underfitting, overfitting. So we need to make some trade-off between variance and bias, so that to achieve a good compromise and give some good results like the best fit here. So we have seen this pattern, like symptom of overfitting or underfitting before, that for the classification, the underfitting doesn't separate the classes well, and the overfitting is trying to, okay, have a very complicated decision boundaries. So those are more likely to be influenced by the random noise. So just right is that, okay, we reach to a good point, we have a no misclassification error, but somehow this can generalize well. So this underfitting, as we said, has high training error, and the training error is also very close to the test error because it doesn't learn well, and it also has a high bias, which means it cannot, which somehow is similar to the high training error, and the overfitting is like an offset. We have the very low training error, and the training error is much smaller than the test error and has a higher variance. So as we can see here, shows the second point. We can actually tell training error, overfitting from the validation error and the testing training error. So probably we can take a 2-minute break before we move on to the regularization. So when we talk about when the model is very complex, we have a lot of features and we have a lot of parameters, but our data is not that much. So this will lead to so-called overfitting. So here is actually some possible solutions for either underfitting or overfitting. So when you face the underfitting issue, you probably want to try a more complex model. Like when you have a lot of data, you can go for a neural network. And you also want to add more informative features. And then probably if you are training training the model, you didn't go through many iterations, probably you end up with underfitting. So this case, you train longer is another option. So when you are facing this overfitting issue, so one way to address this issue is you add some constraint regularization to your model, or on the other hand, you can get more data to make your to increase the sample size. So probably at some kind of stage, the overfitting issue disappears. But in reality, the data is really limited. So we are talking about the regularization techniques in our following slides. So the regularization actually sometimes just mean, okay, we want to constrain the model to make it learn well. Like they don't try to memorize the noise, but they try to understand some pattern in the data. So here is like a 3 different situations for the 3 different scenarios, high bias, like underfit, just right, overfit. So in the first case, it's just too simple. Like we only have a really simple linear model in the model setting. So this one probably will generate less good results, because when your data shows some kind of nonlinear trend. And for the middle part, it has 3 different parameters with some additional feature compared to the first one. So it will generate well, will fit well. So on the rightmost part is that you have a lot of features. And at this time, you have 5 different parameters. So this will give you the overfitting, like they try to memorize, although sometimes it's just a random noise. They try to cover that one in the regression line. So the number of parameters is actually, you can think it's a number of like the degrees of freedom your model can try. So regularization is that, okay, we don't give you too much degree of freedom. And then at this time, the model can fit the data more easily and less easily to be influenced by the outliers. So especially in the reality, it's common that we have the number of features way larger than the number of samples you have. So under that case, the regularization is usually needed. For example, if you are dealing with the gene expression data from human, you have 20,000 protein coding genes, but your samples is usually several hundred. So under that case, the number of features is way greater than the number of samples you have. So you probably will consider, should we remove some features, or should we apply some regularization to the model? So we cannot just tell the model or tell the machine that, oh, can you be less free? Like, can you stay home? We cannot do that, but we can actually introduce the regularization part into the loss function. So this is why when I talk about the classification problem, when I talk about the regression problem, I always emphasize the loss function. So loss function is actually like the guide that you want the algorithm to learn. So for example, you want to ask the model to perform good classification. So we have this loss entropy. I want to minimize the loss entropy. So this is actually, you tell your model, okay, this is the direction you should go. And here in regression, we have the MSE at the loss function. And when we tell the model to minimize the MSE, and then if we want to add the regularization, we simply put some penalization term into the loss function. So for example, for the first one, when we want to minimize this updated loss function, we on the one hand, we want to minimize the MSE, And on the other hand, when we minimize this J theta, we cannot allow this term to be very big. So this in return will make the model to have a smaller theta. And so basically the theta cannot be very huge. So this is one way that we restrict the model to make them have less freedom when fitting the model. So here is like the 3 types of constraints we can apply in the regression, specifically in the linear regression scenario. So one is the L1 penalty. So if you remember the distance we talked about yesterday when we are dealing with the King method. So we talk about this absolute value. It's the L1 distance, and the Euclidean distance, which is showing like a square, it's L2 distance. So here is basically like we give it another name as L1 penalty or L2 penalty. And also there is like hybridization, like it's a hybrid of L1 and L2. It's called the elastic net. And it turns out that like in some scenario, elastic net can have the benefit or can somehow outperform Nassau or Ridge, no? So it's like also some kind of a compromise of those two and like show better performance. So this elastic net is simply using the like a small combination, like R is just a ratio, and it converges from 0 to 1. So basically, you instead of add a L1 penalty or L2 penalty, you add both of them, and they have some weight before each one. So when R equals to 0, that basically means we will have the elastic net regression is a ridge regression. When we have R equals to 1, so it will reduce to the Nassau regression. So yeah, it's just like a hybridization between those two. So if we visualize this part, like what is actually the Nassau ridge or elastic net and how they work. So we can think, okay, if assume we only have 2 parameters, theta 1 and theta 2. So if theta 1, the absolute value of theta 1 plus absolute value of theta 2 equals to a constant. So basically this will give us a square, right? Like in the coordinate system, the usually shows a square. And if it's in the square form, it will always shows to a circle. So basically, when we minimize this J theta, we at some point we will reach that MSE theta plus this penalized term equals to a constant. So that means this one, like which is MSE theta, and this one is the penalty. They somehow meet at some point, and compare this one and the L1 and L2. We can probably feel that L1 penalty will more likely to met at the edge, but L2 will more likely to met at some point, like no, but like theta or theta 2 or theta 1, theta 1 will be small but will not be 0, and in this case theta 1 will be exactly 0. So this actually, like in reality, if you run this L2, L1, and L2 generalization, you will find L1 have more 0 in the theta. So this actually tells, okay, in the finalized model, you have a lot of features is not included in the model, right? Because they have the theta at 0, which means they don't have any influence. Like the theta is a parameter, is a coefficient before that feature. So they don't have any influence on the model. So this actually gives us some kind of advantage, because when we have a huge amount of features, but not all of them are useful when do the prediction, this serves as a form of feature selection. So basically, you don't need to compute the correlation between a feature and the Y in the label. Instead, you just simply run this algorithm, and it will automatically do the feature selection when they fit the model. So this is somehow an advantage. And the elastic net is it's a combination of this one and this two. So it shows like this kind of shape. And in this case, there are some features to have exactly parameter at 0, and some features with a very small parameter. So yeah, it's again like a combination of those two. So far we have covered everything. We have prepared for the regression, that is in total 6 regression algorithms, and the loss function as the mean square error or mean absolute error. And we talk about the overfitting, underfitting, and some solutions if you face this issue. And we also lastly talk about the regularization, how to constrain your model so that they don't overfit. Because when we have a very huge number of features, it's very easy to overfit, especially in the biology. We have a lot of features, and some of them are probably not useful. So we probably will need this regularization from time to time. So in the rest of the workshop, we will talk about the unsupervised learning. So specifically for the dimension reduction and the clustering. So as I said, the unsupervised learning, we don't have the label Y. So it's like we just want to find the pattern behind the data. So for each of the category, I will talk about 3 different algorithms. But in our practice, like when we do the Jupyter Notebook practice, we are only going to pick one, like for example, PCA, because it's most widely used. So we are going to try that one. But you are encouraged to try other things. Simply go to the website and try to run the code on your own. And for clustering, we will practice the k-means. But yeah, I think the most important part is you get a feeling of how this method works. So for the dimension reduction, this is very important in our practice, because when we dealing with the high dimensional data, our human, like we live in the 3-dimensional space and the +1 dimension time. So we cannot actually try to imagine what is like a high dimension because we are like no dimensional creatures. So high dimensional data will sometimes give you a blessing, because sometimes when you have high dimension, so probably there is one feature or some feature that is very useful. But sometimes it's a curse, because when we have this high dimension, we usually run into some trouble, like with the model or with the sample. For example, in this curse of dimensionality, so if we don't do any kind of feature selection, purely just put the training data into your algorithm, and then many machine learning algorithms will find it very hard to find a good solution, because there will be a very complicated optimization problem, and sometimes you track in the local minimum, so the model doesn't learn well. And also, if you put a lot of features, high-dimensional data into the model, so the computation will meet some problem. For example, you have like 20,000 of genes, and then you have several millions of people, and then the memory it requires will be very huge. And also, when you're computing those things, the training speed will be extremely slow. So this is like the bad thing the high dimension brings us. And also, just think a simple case that we have a binary feature. For example, for each feature, it can only take 0 or 1 value. So when you have a number of n features, it will actually lead to 2 to the n combination. So if your sample is fixed, so it's very hard to find a small group of samples to have to share the most of the features, so the data can be like very sparse. So this is also like one drawback for high dimension. To deal with the high dimension problem, one very classic way is to do the PCA. I think probably you guys have heard about it, either from research papers or from talks. So PCA, which stands for the principal component analysis, is that we want to find a projection, or sometimes just use the word projection to preserve the maximum variance. So just take this example. We have this two-dimensional data, which is small, but we want to do the principal component analysis. We want to find a line that goes across the center. And when we make the projections, like we project each of the dot to the line, we want to maximize the variance of the coordinate on this line. For example, here, we can project the data point to C1. So we have this projection. And if we project into other directions, we have a smaller variance. So we want to find this line that have the maximum variance. So when we have this maximum variance, we actually somehow minimize this residual distance. So basically, this is called, okay, we want to preserve as much information as possible. We want less information loss, which is showing as a residual here. And on the other hand, previously we have n sample. Each of them have two features. So it's n times 2, like a memory, or n times 2 space. But after we do the projection, we have one value for each sample. So basically, this can be regarded as a way to do data compression. If you think, okay, you have millions of features, and then you end up with 100 features, several hundred features. So basically, this will reduce the file size a lot and can be efficiently be computed. And on the other hand, when we have a million of features, we cannot imagine what that the feature dispute looks like. So, but if we minimize, we do the PCA, and then we take the first 2 PC, and then we project the sample to this PC space. So we can actually do the data visualization, which is very useful in our daily analysis. So one thing I want to mention is that PCA is a linear method based on the line or maybe a plane. It's still a linear combination of different features. For example, if this if C1 is the principal component PC1, then C1 can actually be written as like the linear combination of x1, x2. So still, PCA is a linear dimension reduction method. So let's go a little deep into the goal that we want to find a orthogonal set of R linear bases. So which is the line we talked about before. So, and then each of the dot have a corresponding coordinate on this line. So this is called the score, corresponding score. So we want to maximize the variance, and which is equivalent to minimize the loss. And this loss is sometimes called the reconstruction error. So basically, we want to minimize this function that we have the x1, xi is the ice sample, which is the original data, and the xi hat is the projected data. So the difference between those two is the reconstruction error. So we want to minimize that. So PCA's implementation is usually using this called singular value decomposition, so that we have n samples and d features. So we can actually write it into a product of 3 different matrices. So first one, it's a U, which belongs to the score, scores of in the principal component component space, and this sigma. Sigma is like a diagonal matrix, like they don't have a value, other elsewhere only have values on the diagonal line. And the V is the principal directions, like the direction we have, like C1, C2. So when we try to like do the PCA, we select the first R pieces. We actually turns out to okay, we select the part in this in this diagram shows. And if you want to project new data onto the current reduced dimension space, we simply can multiply the data with this dimension space. So basically, this will give us the lower representation of the original data. So as I said, PCA is a very useful and very sometimes we call it as a linear dimension reduction method, and sometimes we just want to okay, can we do it in a non-linear way? So one method is called the t-SNE, which is short for the stochastic neighbor embedding, and the T here is like the T distribution. So there is one underlying assumption of PCA is that they assume the data is from the Gaussian distribution, and but the t-SNE somehow like can achieve. They use the T distribution to achieve the local to pay more attention on the local structure, and PCA is more like a global structure oriented dimension reduction method. So the core algorithm in t-SNE is that in the high dimensional space, we want to measure whether these two samples are close labor together. So we have this joint probability of sample I and sample J. They have this Gaussian. They have this Gaussian form probability. But in the lower dimension space, we want them to also like if two data points in the high dimension space, they are neighborhood. Then in the lower dimension, we also want them to be the neighborhood. But here we don't use the joint probability as a high dimension use, but using T distribution derived joint probability. And as I said, we want to maintain the neighborhood relationship after we do the dimension reduction. So actually, it's that we want to minimize the difference between this distribution and this distribution. So this is achieved by a measure called the KL divergence. So if you are measuring in steps, you probably have heard about this before. So this one minimize the KL divergence. It simply tries to make the distribution joint distribution density to be as similar as possible. So this will give us some kind of like a distortion, like the structure is no longer as the global structure preserves. So for example, if we take a look at the difference between Gaussian distribution and the T distribution, so we probably can find the T distribution has a heavier tail. So heavier tail means, okay, if we have the x, like x is like the distance between two points. So if they are close to each other, so in this in this high dimension, they have like a higher value in the joint probability, but in the T distribution, they have a lower. So this will gives a kind of like give us some signal that in the lower dimension, they seems to be more close to each other. But if the distance is far, then we can compare the T distribution and the Gaussian distribution, and this gives us results that if these 2 points are far from each other, then in the lower dimension, they tend to show a larger distance between each other. So in reality, if we test these 2 differences, for example, on the same data set, do the PCA and also do the t-SNE, we can see that they have a very different separation pattern. So this means that it's a data set for 0 to 9, like 100 digits, and we can clearly see that t-SNE seems to have the better separation between each of the digits. So this is just purely based on this dilution, like when we change it from the Gaussian distribution, which is the underlying assumption of PCA, to the T distribution. So those will focus more on the labels, like the local structures. So this is why this pattern is more clear. So these 2 methods, like PCA, is a very classic statistical method, and the t-SNE is invented like maybe 2008, like almost 15 years ago, and yeah, it has a kind of like received a lot of criticism. Like some people think t-SNE isn't actually a dimension reduction method, but it's more like a visualization method, because you want to just want to have this good property that they focus more on the local structure, so you can see the pattern more clear. So some people think, okay, this shouldn't be called as a dimension reduction, but more like a visualization. And more recently, there is a method like still can achieve the nonlinear dimension reduction called the autoencoder. So autoencoder, as we have seen from the name, that it contains the encoding, decoding process. So this method is achieved by the neural network, because we know that neural network is a universal function approximator, and it can achieve the nonlinear function. So it's very natural to use neural network to do that. So consider a signal or simply a voice. If it's just like a pure transition from one place to another place. So it have n features, and then we end up with n features. So this is like not a dimension reduction, right? But what if we try to reduce the number of nodes per layer? So from the output, from the input, we reduce number of nodes layer by layer. It's more like we try to create a bottleneck in the middle, and this one can try to squeeze the information, like if it's a noise. So probably those will be filtered out. They try to squeeze the information into a bottleneck, which is called the lower dimension embedding. And then after that, we try to decode the information, because right now we have a compressed information. We will try to decode to recover the original input. So this part can be actually summarized by encoding process and also the decoding process. So we have the encoding function, which is approximated by the neural network, and then we have a decoder function. It's also tries to be estimated by the neural network. So basically, they tries to learn okay, from this encoding and then decoding process, we want the process can recover the original input. So this is just as the data part shows the original signal, and after this process, the reconstructed signal. So the loss function is trying to minimize. Okay, we minimize the original input and the reconstructed input. So this is simply can be shown that original space is a very high dimensional space, and latent space we have a lower dimension, maybe only 2. We map the data point to the lower dimension and then map back. So this is the idea of autoencoder. So it's very interesting and also very I think very smart to use this so-called bottlenecks technique to do this. So this is about the autoencoder. And the last topic of dimension reduction or unsupervised learning is clustering. So as we talk a lot about the supervised learning, but many of the data in our reality life, they don't have a label, because when we want to have a label, for example, we want to we take a picture like the CT image of the patient, and then we want to label whether this is a tumor or not. We need to hire probably doctors to do the annotation for us. So it's a manual work. But many of the but those time is very how to say it's real. It's very expensive to hire doctors to purely use the domain language to annotate the images for you. So many of the time we don't have those labels. So we need to do some kind of clustering to identify the inner structure in your data. So we, for example, we have a lot of samples. We want to tell, okay, some samples, they are more likely from one population, and some samples, they are more likely to from another clusters. So this is the so-called the clustering, what the clustering is doing. So the thing, some useful algorithms in this clustering is k-means, hierarchical clustering, and the DB scan. So I will talk about it one by one. So for k-means, it tries to assign some centroid and then try to compute the distance between some instance and this centroid, and simply assign the instance if it's close, if the centroid is very close to the instance, then it will have this label at the same at like a centroid at one cluster, something like that. So and then after they do the division, like they can simply stratify the samples into 3 different groups. After they do the stratification, they recalculate the centroid. Basically, they try to calculate the mean of these 4 points, and then this is the updated centroid. And then they repeat the process, like after they have the updated location of the centroid, they do another round of sample assignment, and then do another round of centroid calculation. So they repeat this process until the centralization doesn't change much. So this will generate the final result of clustering. So it's very simple idea, but it's very effective, and it makes quite a lot of sense. So this algorithm is very fast. So although it's done in a sequential way and doing a lot of updating and doing a lot of process, but it's shown to guarantee to converge in a small number of steps. And just as this shows, although we don't have a very accurate centroid at the beginning, but after each time of updating, they will eventually, like only 3 or 4 steps, they converge to a very good position. So this is how the k-means clustering works. But there is a problem is that the k-means cluster, although they can converge to a solution in some finite steps, but they are not guaranteed to converge to the good solution. So this is also called the local optimum. So just to try to fix this issue is that you probably can run these algorithms again or run it several times. Each time you have a different initialization. So after that, you find the best solution and keep the solution. Also, if you have some prior knowledge about, okay, how many, what's the possible location of the centroid located, you can use them to as the initialization in your before you run the algorithm. So those are like the two solutions you can try. And there is some limit about k-means. So first, k-means favors the cluster. Just as the calculation we can see, it favors cluster with a similar size. So in the unbalanced data set, it's probably not a good choice to do it. And also, we need to specify the number of k. So we probably like so for the very first step of initialization, we need to know the number of k's to make the algorithm work. But later, I will in the Jupyter notebook, I will tell maybe teach you guys maybe they actually have some kind of solution that guide us to find the good k, like the number of clusters. So the second clustering algorithm is the hierarchical clustering. So basically here, we do it in the bottom-up approach to form the cluster into a tree structure. And eventually we will end up with just one cluster. So basically what it tries to do is that, okay, at step 0, we treat every sample as a cluster. So they have their own cluster. And then we compute the distance between samples. So this will give us like, okay, we want to know which two samples have the minimum distance. And those two samples should belong to the same cluster. So we will merge them like to form a new cluster. So at the step 1, so we have like updated samples, like these two samples merged together, they form a cluster, and we then try to compute the distance between this cluster to other samples, and then try to form another small cluster. For example, Y and Z, they form to a smaller cluster. So we keep doing this until all the samples are merged into a single cluster. So this will give us a tree that from the very beginning we have all the samples, and then as we go deep to the leaves, we will branch, and then eventually we will branch to a single sample clusters. So how to cut the tree will determine that, how if we cut the tree from here, so then we will end up with a single sample cluster. If we cut the tree from here, we will have 2 clusters. So it's very flexible, and it don't require to pre-specify the k. So this is a very intuitive way to do the clustering, and because we don't require a lot of computation, this one also scales up, scale well when we have a large sample set. So this is a kind of illustration of the previous figure, that we calculate the distance between clusters and the samples, and then match them together. And then eventually we will merge them into a single cluster. So on the right, it's like the relationship between each clusters. So if and this will decide how are we going to cut the trees. If we cut here, we end up with 3. 3 different clusters, and then actually you can play with how many clusters you have, and then you make decisions where to cut the trees. So the last clustering algorithm is a DB-scan. So it will define clusters based on the density. So for example, we have a lot of samples in some local region. So it will try to compute within some kind of local distance how many, like if there is a sample within this distance. So we treat them to be the same clusters, and they eventually will iterate all the samples and form into different clusters. So at the right figure shows this kind of thing randomly, first randomly pick up a sample and calculate the distance, like find the samples within this distance range, and then assign those samples at the same cluster as the current sample, and then grow. So basically, at the smile face shows the outer circle will all belongs to the same cluster, and then after we finish the outer circle, then it will randomly pick another and assign the samples, and then also tries to assign clusters. And then after that, we move on to the next part of samples. So eventually, it will try to find the subregions that have the very high density. And it works pretty well. If your cluster is very dense, that means you have a lot of samples that are very close to each other. And if the clusters are well separated by the low density regions, so this DB-scan is a good way to go. And it's very robust to the outliers because it only depends on the smaller distance, local distance to other samples. And the computational complexity is also acceptable and times log m. So m is the number of samples in your data. So I think that's all for the theory part. So just from the past 3 days workshop, we have the knowledge about machine learning's definition and categories. So we have the impression about the workflow and about how to train a machine learning model and make it work better. We know the rationale of several very popular machine learning algorithms, either supervised learning or unsupervised learning. For supervised learning, we have classification, regression. Unsupervised learning, we have the dimension reduction and the clustering. We also know how to measure the performance for evaluating different machine learning algorithm or models. So after we know the performance measure, we can actually use it to decide which algorithm we should use. And we also learn the challenges in the machine learning, especially the overfitting, underfitting. And we learn what kind of solutions we have if we want to address the issue. And we also have experience in the Jupyter Notebook and NumPy and many other packages. We also have the experience with how to build, train, evaluate a classifier. And for the regressor, this is our task today. That we go to the Jupyter Notebook. So if you are new, you can just open your terminal, try to get a clone that QC Bio. Let me try to find it. QC Bio GitHub repository. I think it's not here. I might just see this GitHub file. So if you are new here, you can just try to go to the GitHub link, which is I think on the day 1 slides. So it provides a link, and then you go to your terminal. So git clone this link to your own local computer. So after that, you will have QC Bio and machine learning with Python folder. You enter into that folder. So if you are like git clone the repository several days ago, you can try git pull to fetch to get the update. And if you met some problem with git pull because there is some changes, so you can try the git reset hard and git pull again to clone the day3 folder into your current folder. So I will just pretend everything is up to date. So for example, if you git pull for the updates, and then with the already up to date, then you can launch the Jupyter notebook. So we will use it to practice the regression and the dimension reduction and supervised learning for today. Yeah, for today's coding. So this is the day 3 Jupyter notebook, and then you can take a look at the table of contents. We have the several sections. So first, we are going to work on the regression, and then we move on to the regularization. So because I think those 2 parts is still very important in our daily research. And then we will talk about the PCA and k-means as a representative for dimension reduction and clustering. So we probably just go through the notebook from the top to the end. So for the regression, here I just prepare some example, which is linear combination. Like we first define how many samples we want to generate, try to do a simple simulation, and what's the coefficient and the intercept for the linear model, and then we generate like randomly generate some x and generate some the error, and then we based on the linear model, which is y equals 0.5 times x plus the intercept or bias term and plus the error. So after that, we just simply plot the data out. So we can see, although there are some kind of fluctuations, but the data x and y, they have a clear linear pattern here. So we are going to use a linear regression to model to maybe fit the data and see whether the fitted data, like a fitted intercept and the slope, equals to the previous setting, the true value. So first, as usual, when we have the data, we usually split the data into training and testing. So here I split them based on the 1/3 at the testing, 2/3 of training. Here I set the random state to be a fixed number to ensure the reproducibility. So after that, if we want to train a linear regression model, we simply from the sklearn linear model import the linear regression, and then we build this model, simply call this function and fit this model. As I said yesterday, the sklearn, they have a very consistent interface. So as you can see, for regression, the usage is very similar to the classification. So after we do that, we can try to visualize the fitting. So simply in this case, it's just trying to plot the fitted line on the original data. So what we do here is that we create the next sequential x, and then for each of the x, we use a model to predict the y. So this is if we plot them with a line, this is our regression line, the fitting line. So this is exactly what we have in these two lines. Try to get a x based on, okay, we start from 0 and 10, and then we have we generate like a series of x. Using this x, we can get the predicted y. So this is our fitted value. And then after we try the fitting, the model, actually we can go to the attributes to see what's the coefficient it fitted. So for this model, or for skname, if it's calculated attribute, they usually have this underscore suffix. So we can simply just print them out. We see that the coefficient and the intercepts, although they are kind of different from the original setting, which is 0.5 and 2.2, but they are close enough. So we probably can think based on this line and also the coefficient intercept, we can see the fitting it's doing a good job. So yeah, I think probably we can take a 10-minute break, and then we will go over the next thing. So for the regression, we want to measure how well the model fits the data, and we can perform this kind of like a calculation to calculate the R-square. So probably you have heard about it before, which is a measurement about how well the linear model fits to the prediction data. So R-square's definition is 1 minus the residual square, sum of residual square, and over the total variation. So as we can see, if the data, the model fits the data perfectly, then this part will be 0, the R-square will be 1. On the other hand, if this model doesn't capture any variation in the data, so for example, the denominator is equal to the numerator, then this will be 0. So R-square will be this will be 1. R-square will be 0. So basically, R-square is a measure to quantify how well your model explains the data. On the other hand, as we have said before, we can use the MSE or MAE to measure the performance. So luckily, you don't have to calculate them by hand. You can just from the skname matrix import those scores. So here, it's just we want to evaluate how well the model can fit the data on the training data, and then how well it can generalize to the test data set. So here I just try to run it with different R-square, which usually R-square greater than 0.9 is a sign that the model do a pretty good job. And there is also an interesting phenomenon that the R-square on the test data set is smaller than the R-square on the training set. So this is somehow expected, because we know the training set they always have some kind of tendency to be overfitted. So usually we will observe this phenomenon. So the next one is the polynomial regression. So to do that, we actually just tries to create a new feature based on existing feature. So here is what we tried in this one, that we manually create a new data set that the y is a linear combination of x and the x square and plus the intercept and the error term. So if we plot the data set, we can see the trend that nearly the target, which is y, have some kind of nonlinear relationship with the feature, which is x. So still, whenever we have this data set, we split into training and testing. And this time, we will try to fit the model just using a simple first using a simple linear regression first. But here is that we actually do the adding the feature as adding the x square as another feature. So this is what we did. We construct the feature set based on contains the current x and also contains another, which is x squared. But you can also do it using the package. There is a package called polynomial features. So simply you create this transform. So basically, this one will tell when you run the fit transform. This one will automatically create the x squared based on the input of your x. So yeah, basically these two options are equivalent. So probably you can try on your end and compare if there is any difference. So after that, we just run the linear regression because we have the x and x squared as a feature. So basically those polynomial linear regression is reduced to a very simple linear regression. So this is what we do with the fitting. And we actually can also, after fitting, we actually can print out the fitted line and also the corresponding parameters in this model. So here, the red curve is the fitted line. We can see that the curve captures the trend well. So besides that, besides just inspecting the fitting in the data, we actually can plot the learning curve. So basically, what this does is, okay, for the training data, we somehow every time we just set incremental, like next time we use m samples in the fitting, and the next time we use the m+1 samples in the fitting. So that at each time we still measure the training error and the test validation error. And this will give us the so-called learning curve that along as the training set size change, how the MSE change. So as we can see that the training and the validation, they will become very stable as the training set increase. And there is also a tendency that the training MSE is smaller than validation. So this is as expected because we know the training can be overfitted, but so they tends to have a lower MSE. But we can also observe the two curves. They don't have that much of difference. So this in general, the data, the model generates well. So there is not much overfitting issue. So here is an exercise, but I think you guys can try it later with your own, after the workshop. So let's go to the support vector regression. So here is still that we can run the support vector regression on the previous data set. So here is what we can try is that we can use a linear support vector regressor, or we can use the polynomial SVR. So the linear SVR is imported using this, it's created using this function. The epsilon is just specifying how large the margin is, the street is. And the SVR itself can support the kernel trick. So here we use the polynomial, just putting the pointing into the kernel as a parameters. And then we can use the degree because we use the x square. So this is a degree of 2. And the C is a hyperparameter that tries to tell how sensitive we should the model should be to the violations, margin violations. So we just set it at 100. So after do the fading, and then we can still as the previous we did do the plot the fading. So for the single SVR polynomial, because this is we use a kernel tree, polynomial kernel tree, so it captures the data trained well. And if we just want to compare how the linear SVR and the polynomial SVR behave, so basically we can see that the linear SVR is basically cannot capture the curve very well. So we probably can claim this linear SVR is underfitting, but the polynomial one seems to perform pretty well. So later, for the third section is the model regularization, which is the L1 penalty, L2 penalty we discussed in the slides. So we use this regression exercise dataset, which is on the day3 folder. You can simply run the code to import it into the Python. And then we split the data into training and testing. And we take a quick overview how the data looks like. So we can see it's clearly not a linear relationship, but somehow like a likey icon or something. But yeah, let's just try to first fit a simple linear regression. And here, after we plot the fitting, we can see the line somehow the straight line doesn't capture this part. So this is like a huge violation to the model. And if we try to fit the model using polynomial, for example, we rise up to the 20s. So which means we will have a lot of features in the model. And let's see how the data will behave. Let me see. Yeah. So and then we fit the x polynomial. Yeah. With the y. And then we can check how the fitting looks like. So as expected, this data, it seems like to capture all the variation in the training, and as the curve shows, it clearly shows a overfitting thing or overfitting signal. But yeah, the golden standard is that you can try to predict on the test data, and then compare the MSE between training and the testing, and you will see it's overfitting. But here I'm not doing that, just inspecting the curves. You will see the model overfits the data in a large scale. And if we reduce the polynomial to degree of 5, we probably can see that the curve follow the trend pretty well. So this is a good fit. And for the d equals to 20, degree equals to 20, we can actually make it better by using this regularization techniques. So specifically, we can use the ridge regression that we add a penalty to the beta square, the L2 norm of the beta. So here is what we did, that we can simply import the ridge module or ridge function from the linear model. And then this is just trying to prepare the original feature set that we have the polynomial of 20. So when we try to run the model, we simply use the ridge set alpha equals to 1, and then fit the data. And here we will check the results by showing the fitting. And here we still see there is some kind of deviation when X is small, but we can adjust the alphas, which is the hyperparameter, so to make it a bit better. And we can also check the model's parameters by run the model.coif and with the underline here. So here it shows for those 20 features, which the corresponding weight of each feature in the model. And lastly, we can try to measure the MSE on the test data. So the MSE is pretty small compared to the bivalue. So this tells us the ridge regression is generalized well to the test data, which the training has never seen before. So another technique is called the Nassau that we go over in the slides. It's just the L1 penalty, and we can simply fit the important Nassau and add the alpha at the hyperparameter and fit the model. So this one will shows how the fitting it's doing. So and then we also very similar to what we did with ridge, print out the model coefficient and print out the MSE. So one exercise is that previously I want you guys to compare the coefficient of Nassau and the ridge and what you found. So here I probably just directly give the answer that on the Nassau regression we observe a lot of zero, which means these features will have no effect on the model itself. But on the ridge regression, we cannot see those zeros, but we do see a lot of small. We do see a lot of those small weight, and the Nassau regression simply will constrain the model, like don't allow them to have small weight. Simply will press them to be zero. So this is like doing some feature selection thing in this model. So another thing is that how can we tell the hyperparameter is a good choice or not? So actually you can try to run the whole process by specifying different parameter, just using some for loop. You specify the hyperparameter choice. And but also there is another thing I think you guys can check out for the grid search CV. So basically it will use the cross validation to help search the best parameter you specified. Here I didn't, I'm not going to too much details, but specifically if you have a lot of parameters, for example, you have 2 hyperparameters and each of them have 5 candidate choice, then you have 5 times 5, 25 combinations to try. So probably you will find it a little difficult to do it purely writing by your own. So you can use the grid search CV, simply specify the hyperparameters value, and then allow the function to do it for you. So this is very convenient to use. So also you can check out the nesting net. As I said, nesting net is a compromise between Nassau and the ridge regression, the penalizer regression. So it probably give you a better performance. So you can try later with your as an exercise. So we move to the fourth part, which is the dimension reduction. So here in this two-pattern notebook, we only focus on the PCA because it's the most widely used. And I think we are going to focus on the handwritten digits. So this particular data set only contains digits 1, 5, and 6. And each image is 28 by 28, in total 784 84 value for each image. And the values can range from 0 to 255, which is like the pixel density. So if you are want to find more, you can check out the link. So this is the overall example for the handwritten digits. So each digit is a 784 vector, and it has an associated label denoting whether it's 0 or 1. And sometimes the hand digit doesn't well written. For example, this one, we probably have a hard time to tell whether it's 6 or 4. So yeah, it's a very ideal, not ideal, like it's a very classic benchmark data set if you want to evaluate the machine learning algorithms. So what we did is just try to load the data into a Jupyter Python environment, and then try to check out what's the data structure looks like. So the number of training images is pretty big, 16,000. So this is great. And for each of the image or sample, they contain 784 features. So compared to the sample size, I think it's a great data set that you can actually run a lot of algorithms on. For example, you can train a neural network to to classify the digits, because we have a very huge sample. So I would say it's probably great to do that, because we know that neural network is very data hungry, that it always requires a very huge number of data set samples to perform well. So we continue to just randomly pick one feature and display it. So you can, what we do here is that each of the images is represented as a vector with 784. So you can reshape it to be a 28 times 28 matrix, and then you use the IMShow to show the image. So here, with the corresponding label. So here it's a 6. So it's doing a good job. The label actually matches with the pattern. So, and then if we look at the train wise, the label actually is a one hot vector. So one hot vector means, okay, in this vector there is a 1 in some position, and all the other positions are 0. So this one is it's trying to indicate the seventh digit is the label. So because it's from 0, 1, 2, 3, 4, 5, 6. So this vector actually shows this image. It's 6. So this is a one hot encoding. So, but later I think like probably we just try to convert it to be a label. So basically for each image, we only have the one single value that are showing what's the number. Like here we use the NP word train y and extract the actual labels. So right now we don't have a vector for each data point, but we have one single value for each data point. So here is what we do with PCA, that because right now the value are all from 0 to 255, so we don't do the scaling here. But if you are doing it with your own data set and the feature, they have a very huge difference in the scales. You probably want to scale them to the same scale, and then also sometimes you probably will do the standardization, which means you want to divide by the standard error before running PCA, because PCA is kind of like it's not invariant to the scaling. So usually we found the results looks better after scaling. So here it's what we perform, that we import the PCA and then initiate this object and then fit the training data. So remember that although the imaging test data set is enabled, but here we treat it as an unsupervised learning problem. We don't put any training labels into the fit. So here, when we call the fit method, it will perform the PCA for us. So as you can see, it runs a little while, but overall, the computational efficiency is high. We can access the explained variance for each principal component by using the explained variance ratio with the underline. So just running it, it will output the corresponding value for each PC. So this explained variance ratio is actually showing how important this PC is among the data. So this value is like in a decreasing order. The first PC always explains the most variance, and we can actually plot the explained PC using this plot, and we can clearly see the first one is explain the most variance, and then they drop down to somehow very close to 0. And if we zoom in from, for example, 0 to 30, we see that they have a huge drop in the very first several PCs, and then they slowly decrease to some level. So when we talk a bit about PCA, it's always like how many PCs we should choose. So one simple rule is that, okay, we want to choose a PC that matches to like cumulatively jointly can explain more than 80% of PCs. So here is how we choose a PC that we can simply run this line, try to calculate the cumulative sum of all ratio, and then try to find at which position this cumulative sum is greater than 0.8, so 80%. So this will give us 34. So basically means we probably can, if we trust that the left 20% is the most likely to be noise, then we can just simply use the top 34 to do the downstream analysis. For example, we can use a PC as an additional feature to train a classifier, which we will later do in the classification part. So another option is that we can try to plot the cumulative sum as a function to the number of PCs. For example, we can from this figure we can plot the cumulative sum at the number of PCs increase. So there is a point that before this point the increase will be quite fast, but after that the increase is very slow. So this is called the elbow point. So some people use this this method to find how many PCs we should keep. So one good thing about the dimension reduction is that we can transform the high dimensional data to a lower dimension and then do the realization. So here is what we did, that we simply call the transform function to the original train X data input data. So this will perform the projection, like to project the original data to the principal component space. So after that, I just simply choose the data that is either 1 or 5, and then try to plot them in the PC1 and the PC2 space. So after we run that, we can clearly see some dots, like the kind of, although they are kind of adjacent to each other, but we see there are some patterns. So probably one, like the red one is it's showing the digit 1, and the the blue one is showing the digit 5. So this is how we can visualize the 784 features into summarized into chapter 2, and then we can do the visualization. So as I said, that the PC we got can actually be used as a feature for the classifier. So here is the example that we actually just use the first 2 PC as shown here, and then put it into a random forest classifier. So after that, we evaluate on the test data set, it can achieve 2.93, 93% of accuracy. So which shows it's pretty good. Just keeping the first 2 pieces, we don't lose that much of information. So the last point is last part is clustering. We actually use the k-means like the example that we have seen that we in the data set we contain 1, 5, and 6. So we know the case is that the number of k is 3. So we simply input the number of cases, number of clusters as 3, and then run the k-means to fit the training data. So after we do that, we can call the predict function to get a prediction of whether this sample belongs to 0, 1, 2, which cluster. So after that, we can also visualize the clustering results by putting them into the same figure and then giving them the different color. So this is what we get. The one cluster 1 and 0, 1, 2 is showing in the PC1, PC2 space. So we can clearly see this is like three parts, 3 different segmentation. So basically, this shows we can like use the PCA using the k-means to tell which cluster this sample belongs to, and to access whether the k-means do it well. For example, you can try to compare the cluster purity because we have the label like the digit label, so you can actually compare the cluster and the label to see if k-means do a good job in dividing the sample into 3 good clusters. So anyway, so when we have the number of k, everything will be simple. In many cases, k is not known. So we can actually use an alternative approach called the SILUT method to find the most potential case. So basically, this is the procedure we try that we can import this score function, and then we specify a k-max, which means how many, what's the maximum value of the k, and for each k, we run the k-means clustering algorithm, get the score, and then we plot the score across all the clusters. So basically, we can see that when k equals to 3, which is a true cluster, the score is the highest. So yeah, this one is can serve as a guidance that we probably should use 3 and then run the k-means algorithm to cluster the samples. So I think that's all for the Jupyter notebook practice, and I hope it's useful that you can practice based on the code template I provided you. And although we didn't cover some like Disney, or we didn't cover the other like DD-scan clustering, but I think you can find them easily on the documentation. And using this data set, you can try to run them on your own. So let's go back to the let's go back to the slides. So so far we run everything we have on the Jupyter notebook. So basically we know how to train, build, and evaluate a classifier or regressor. We know how to tune the parameters, either using the specified hyperparameters or the grid search cross validation to find the best parameters for you. And then we also have experience with the unsupervised learning specifically for PCA and k-means. And I encourage you guys to try other things that is not on the Jupyter notebook. So this is like the summary of all the 3-day learning thing that we covers 9 different supervised learning algorithms for either the classification. But this in this category, we cover the 6 different regression algorithms, and for the dimension reduction or clustering, we cover 3 different algorithms for each. So there are also some other algorithms available in the field, and also those are very interesting. But I think for most of the time, you probably can try the traditional, like the algorithm we covered, and see the performance, and then decide whether you are going to use it. So there is still like one single question that after we learn so many algorithms, how should we know which one we should use in our specific problem? So actually there is no way to know that ahead. I would think, okay, based on your data, you select some promising algorithms based on your understanding, try them all, and then you calculate the performance and then find the best one. Because there is no one single algorithm that outperform others in all cases. It's very problem specific or data specific. So otherwise we don't need to learn those algorithms, right? We just learn the always perform best algorithm. So, but there is some kind of guidance to choose an algorithm. For example, if you have a lot of data is plenty, you can simply go to the neural network one because it's data hungry, and it's more complicated, have more ability to learn. But when you don't have that much of sample, you probably should choose from a more simple one and then increase the complexity step by step. And so this workshop, we predominantly focus on the machine learning algorithms, tries to give you a mindset of how they work. But there are still some other things that we haven't covered, and I think it's also important, but it's not our focus. It's that we want to formulate about the problem formulation, like whether you want to formulate into a classification problem, or you want to when you have a numerical value, you want to do the bin treat it as a classification, or you want to treat it as a regression problem. So you will need a different way you formulate the problem, the different algorithm you have, algorithm choice you have. So they should perform differently. So yeah, I will always think the problem formulation is usually the most important part. And also, sometimes in reality, we don't have that much kind of clean data. For example, what we tried on the Jupyter notebook, the toy example we tried is already cleaned. So in reality, you probably have some difficulties. For example, you have missing values, whether you should choose to ignore the feature or you choose to ignore the instance. You need to make some decisions. And for the feature engineering, this is also important. For example, sometimes you don't have meaningful features, or you have a lot of noisy features that it's not helpful for the machine learning algorithm. You need to do some kind of filtering in action. So those are also something important you should keep in mind. So among all the steps, I would always have a impression or have some kind of mindset that the data and the feature actually they jointly decide what's the upper bound of your problem. So choosing different machine learning algorithms is just trying to approximate, like trying to approach this upper bound, but it's the data and the feature that determines what's how high you can achieve. So I would say those like data feature thing and also the problem task thing is very important, and we cannot cover them. So this is more like what we did is the tip of the iceberg, and actually there are some other things you should consider. So, and also I want to mention whether like after this workshop, when you are dealing with the machine learning problem, try to build your own model and run your own code. And you probably will meet some difficulties. For example, you don't know how to use one function. So I would always suggest that Google is the best way to try. And still for the specific machine learning problem or coding problem, you can try the Stack Overflow or the cross-validated thing. And towards the data science, it's a blog website. So it has a lot of like blogs trying to explain what is PCA and from the very beginning, how to train a random forest classifier. So you can always refer to those blogs. And you might notice I have a lot of figures in my presentation, and those figures it's usually adopted from those blogs. And if you want to know more detail about the machine learning algorithm, and also but you don't want to like spend too much time in reading a textbook, you can go to the 3 Blue 1 Brown to learn and also the StatQuest. So they have some good videos to explain the rationale of algorithms. Those are very useful resources, I would think. So lastly, I think that's the end of the workshop. So just wish you good luck and have fun with the machine learning. So actually this figure is generated by AI itself, not me. So somehow, I have the input. I just input a sentence, good luck and have fun with machine learning, and then the AI draws a picture for me. So it's if you are interested, you can go to OpenAI, and there is the E2. So and probably you can just sign up using your phone number. For example, this is what I did. Like just during the break, I told the AI to draw a picture that I have 2 suns in the sky. So basically, one of the figures it generates is exactly what we asked for. So yeah, it's very exciting at this time of point that AI is achieving many tasks more and more useful for us. For example, if you are working in the art industry, AI can help you to generate some prototype, like a framework for you, so you can use the materials from AI to polish them to better serve you. And I think it's a very exciting field to witness and use those products. So yeah, I think that's all for our workshop. So I will stay here for another maybe 7-8 minutes for questions. But, yeah.